What specific problem does the new method aim to solve?
The new method aims to solve the problem of inefficient and impractical open text embedding models that cannot compete with closed source models in terms of performance due to their large size and dimensionality. The goal is to provide a high-quality retrieval model with fewer than 1 billion parameters by training a suite of high-quality embedding models. The method focuses on optimizing retrieval performance by leveraging data-centric experiments and developing the Arctic family of text embedding models. These models are trained to achieve state-of-the-art retrieval performance for their size context window class on the MTEB leaderboard, addressing the lack of efficient and effective open text embedding models that can rival proprietary offerings like Cohere's Embed v3 or OpenAI's Text Embed 3 Large.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, Arctic-Embed, works through a 2-round training process using a suite of embedding models of varying sizes. In the first round, large-scale contrastive pre-training is conducted using a dataset of pairs of queries and relevant documents with in-batch negative examples. This round aims to achieve large-scale training with a focus on batch and total dataset sizes. The training utilizes the InfoNCE contrastive loss and GPU parallelism to optimize performance. The learning rate is adjusted using a linear warm-up and decay schedule. The document sequence length is set to 256 for large-scale training. Source stratification is implemented by filling each batch with data from a single source, contributing to accuracy gains. In the second round, quality-focused contrastive training with curated negatives is performed using the fine-tuning dataset, which includes explicitly labeled negative examples. The sequence lengths are truncated to 512 for queries and documents for all models. Each batch includes 1 positive document and 10 hard negative documents. The learning rate decay schedule is applied similarly to the pre-training stage. Additionally, a tunable hard negative mining strategy is employed to identify and score the hardest negatives for each training example, with an upper threshold applied to discard the hard negatives. This approach allows for effective learning during the fine-tuning phase. The efficiency of the training setup is optimized for computational budget, experimental throughput, and iteration speed, ensuring high efficiency and maximum feasible batch size. Through careful implementation and optimization, the Arctic-Embed method achieves state-of-the-art retrieval performance on the MTEB leaderboard by leveraging data-centric experiments, synthetic data creation, and tunable negative mining strategies.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the method described in the paper include 1. State-of-the-art retrieval performance. The method leads to state-of-the-art retrieval performance for text embedding models on the MTEB leaderboard, showcasing its effectiveness in information retrieval tasks. 2. Efficient data organization. The method emphasizes the importance of data sampling during training and negative mining techniques over simply scaling up data size and batch size, demonstrating a more efficient approach to improving retrieval quality. 3. Innovative synthetic data generation. The method introduces a novel technique for query generation grounded by mined hard negatives, which proves to be more effective than traditional approaches, enhancing the quality of the generated data and ultimately improving model performance. 4. Tunable hard negative mining. The method employs a tunable hard negative mining strategy, allowing for the identification and selection of the most effective hard negative examples for training, leading to enhanced learning and improved retrieval results. 5. Efficiency in training. The method focuses on maximizing experimental throughput, iteration speed, and batch size efficiency, ensuring effective training within computational constraints, which is crucial for practical implementation and scalability. 6. Quality-focused training. By curating datasets through quality filtering and consistency checks, the method ensures that the training data is of high quality, leading to better model performance and more reliable retrieval results. 7. Source stratification. Filling each batch with data from a single source during pre-training significantly improves model quality, showcasing the importance of source stratification in enhancing the effectiveness of the training process. 8. Longer truncation length. Using a longer truncation length for documents during training results in a substantial improvement in retrieval performance, indicating the practical benefit of considering sequence length in model training. 9. Synthetic data creation. Leveraging synthetic data creation to construct additional datasets enhances the availability of high-quality examples for training, improving model performance and addressing data scarcity issues. 10. End-to-end ablations. The method conducts thorough ablation studies to understand the impact of various factors on model performance, providing valuable insights for further optimization and refinement of text embedding models.
How is the method validated or tested?
The method is validated or tested through a series of ablation studies conducted throughout the paper. These ablation studies probe the effects of various factors such as batch size, sequence length, base model, training data, and negative mining thresholds on the model's performance. The results of these ablation studies are tabulated and analyzed to understand the impact of different components on the retrieval performance. For example, in the pre-training ablations, the effects of data sourcing, longer sequence length, and source stratification on model performance are investigated. Additionally, in the fine-tuning ablations, the importance of the tunable negative mining approach and the threshold parameter in filtering out two hard negatives is demonstrated. Furthermore, end-to-end ablations extend the analysis to study the effect of training data on the final score by conducting fine-tuning steps on different configurations of data and base models. These ablation studies provide insights into the key factors influencing the model's performance and validate the effectiveness of the proposed approach through systematic experimentation and analysis.
What results were achieved with this new method?
The new method achieved state-of-the-art retrieval performance for their size context window class on the retrieval portion of the MTEB leaderboard. The suite of embedding models, Arctic-Embed, delivered high-quality retrieval models with fewer than 1 billion parameters. The method demonstrated the importance of data organization, showing that improvements in retrieval quality are more strongly tied to data sampling during training and the method of negative mining rather than scaling up data scale and batch size. The novel technique for query generation grounded by mined hard negatives was found to be more effective than straightforward generation approaches. The method also involved training models of varying sizes from BERT-like backbones and leveraging a tunable negative mining strategy to construct a focused dataset for training. Additionally, the method utilized synthetic data creation to construct additional datasets that benefited downstream performance significantly. The approach of tunable hard negative mining and the use of curated negatives in the fine-tuning stage were key components of the method, leading to improved model quality and performance. The method also focused on efficiency, maximizing experimental throughput, iteration speed, and the maximum feasible batch size to ensure effective training. Overall, the new method resulted in significant improvements in retrieval performance, outscoring previous models on the MTEB retrieval benchmark by a substantial margin.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the potential challenge of data scarcity for high-quality examples suitable for fine-tuning, which necessitated the use of synthetic data creation. While synthetic data construction helped improve downstream performance, generating high-quality negative documents proved to be more challenging than generating synthetic queries. Additionally, the tunable hard negative mining strategy employed during fine-tuning required careful parameter tuning to determine the optimal threshold for maximal learning effectiveness. Furthermore, the choice of model initialization, specifically starting from a pre-trained retrieval model, did not significantly impact the MTEB retrieval score after pre-training, suggesting that other factors may have a more substantial influence on performance. Lastly, the efficiency of the training setup, while optimized for computational budget and experimental throughput, may still have room for improvement in terms of maximizing iteration speed and batch size.
What future work do the authors suggest?
The authors suggest several avenues for future work based on their findings. Firstly, they propose exploring the impact of curriculum learning on training embedding models by ordering data based on the difficulty of negatives. This approach could potentially lead to even better results in model performance. Additionally, they hint at the potential benefits of adjusting the training recipe specifically for long context support, as their M-long variant showed promising results on the loco benchmark, despite not being trained with long sequences in mind. The authors also mention the importance of further investigating the effects of different threshold values in tunable hard negative mining during fine-tuning, as optimal thresholds significantly impact model performance. Lastly, they suggest delving deeper into the impact of training data on final model scores through end-to-end ablation studies, as seen in their experiments with different data and base models in the fine-tuning phase.